In order to keep this video a little on the shorter side, because I'm really just going to kind of state and briefly discuss these properties of parallelograms, I've already kind of pre-written them out for us here, and I'm just going to kind of reveal them one at a time and just briefly comment on what that might mean in terms of what you'll be expected to do for different problems. So, given here a poor sketch of a parallelogram, we'll pretend that that's actually one. The ideas that we're going to look at, we'll start here with our first one, are that our opposite sides of a parallelogram are always going to be congruent. And so I've labeled to the side here AB is congruent to DC, or rather segment AB is congruent to segment DC. And so that's saying the top and bottom are congruent. And then segment AD is congruent to segment BC, so the left and the right sides of this parallelogram, if you want to call them that, would be congruent. Now, congruence, while it means a subtly different thing than equality, for a problem, this right here really is going to tell me that if I knew what this length at the top was, and let's say I was given some algebraic expression down here, let's say this was 10, and this was 2x, I would know that x would have to equal 5, because this bottom would have to also equal 10. So those are the kinds of things you might see show up, where they'll ask you to solve for some kind of value, or maybe they'll both be given as algebraic expressions, and you have to solve and figure out what that side length actually is. The next statement is very similar, except we're focused on the angles, so you may see the same sorts of problems show up here. Angle A and angle C are both obtuse angles that are congruent to each other, and likewise angle D and angle B are both going to be acute angles that are congruent to each other. So you'll have a pair of obtuse angles, a pair of acute angles. In a rare case, you could have them all be 90 degrees, but I'll just point out that if they were all 90 degrees, you would just really be working with a rectangle, most likely. Well, definitely, I should say. A kind of interesting fact that comes out of this is that all of your consecutive angles end up being supplementary. So for this, what I mean by consecutive angles are angles that are adjacent to each other. So angle A and angle D are adjacent, they're consecutive. Angle A and angle B are consecutive. B and C here are consecutive, and then of course D and C. Now supplementary, I made a note here, that means the sum to 180 degrees. So your setup for these types of problems will look something like this. Whatever they give you for those angles, you'll just add them together and set them equal to 180 degrees. Okay? And stay tuned for future videos, of course. We'll see these as problems to look at. So I already actually mentioned this statement, which is good. If any angle is a right angle, it turns out all of the angles will have to be right angles. And that's a combination of these two previous statements here, really. Because the opposite angles have to be congruent. So if your opposite angles are 90 degrees, the consecutive angles would have to also be 90, because A and D would have to add up to 180. If I tell you angle A is 90, well, that makes angle D equal 90. And as I mentioned, that would cause this to be a rectangle. So that's a good distinction to make. So 5 and 6 both deal with diagonals. So I'll just go ahead and pull this out of the way completely. We have the statement here that diagonals bisect each other. So here, my diagram for that, for my fifth option, that both diagonals bisect each other, is that these smaller pieces would have to be congruent. So this segment from A to C is being split in half perfectly by this point E in the middle. So A to E would have to equal E to C, or rather they're congruent segments. In the same way, this point E in the middle, this point here, is splitting DB in half. So the distance from D to E would equal the distance from E to B. So segment DE is congruent to segment EB. And then a final statement, which I feel gets used least often, is just the fact that if you take a diagonal line and split the parallelogram, it's going to create two congruent triangles. These two triangles are exactly the same. One's just been kind of rotated or flipped and that kind of thing, however you want to look at it. The biggest thing about this point here is that it goes back into proving, or at least relating, our area formulas for a triangle and for a parallelogram. Because the area of a parallelogram is always going to be base times height, but the area of a triangle is 1/2 base times height. And that's because every triangle in existence is half of some parallelogram that exists. So it's half of the area of the parallelogram, which is that whole base times height. So stay tuned for other videos if you'd like to see some examples of problems that use these properties to work.